Today, what we're going to look at is the Ray model of light. So we've been talking about light for a few days now, and we've talked about two models in particular. So the first one was called the wave model. So with the wave model, we looked at the electromagnetic spectrum, and we also looked at the wavelength and frequency of the wave itself, right? So remember that the speed of a wave is the frequency times the wavelength. So we could then calculate the wavelength like this, C over F, and then we could calculate F as C over lambda, where C was the speed of light. From there, we were able to look at the different kinds of electromagnetic radiation, such as visible light, ultraviolet, infrared, X-rays, gamma rays, infrared, microwaves, and radio waves. After that, we were talking about the photon model, or I should say the particle model. So the particle model was what we were talking about, the particle known as the photon, which is a single particle of light. And we were able to look at its energy, HF, which came from the theories from Max Planck and Albert Einstein. So what I want to show you today is a simpler model of light, which is the Ray model. So the Ray model is going to be based upon, well, not based upon, but rather I should say this thing that we're going to be talking about is based upon the Ray model, which is geometric optics. So geometric optics is obviously going to be dealing a lot with geometry. It's very simple geometry locally. So we're going to be dealing with reflection and refraction, as well as mirrors and lenses. So today we're focusing on mainly reflection. And we're also going to be looking at flat mirrors. Now we can have flat mirrors as well as curved mirrors, right? So they're either going to be called concave or convex. But today we're going to keep it simple and just look at the flat mirror. Okay. Now, let's say that we have a smooth, shiny surface, right? Think of it like a polished piece of metal. When we have that type of surface and light rays are incident on that surface, so when I mean by incident, I mean that they are literally coming onto the surface, we have something known as specular reflection. So specular reflection is when all of those incident light rays are perfectly reflected off of its surface like this. So whenever you have a very still body of water, a mirror, or something very shiny and polished like a piece of metal, you will see mostly specular reflection. Now let's look at the other type of reflection, which is known as diffuse. Diffuse reflection happens when you are dealing with a rough, dull, and uneven surface. So imagine that you have those same incident light rays from before, right? At each point that those light rays come into contact with the surface, since the surface is kind of pointing in all kinds of different directions, those reflected light rays will also point in a bunch of random directions. So what that ends up looking like to someone observing this is just a very not clear reflection. So it's not going to be useful, let's say, if you wanted to use it as a mirror. So an example of diffuse reflection is if you have a mirror that's super old and dirty. That surface, if you look at it at the very, very microscopic level is very, very rough and uneven, causing those light rays to scatter all over the place and you not able to see your reflection very clearly at all. So I want to talk about in more detail about what happens when you have very, very good specular reflection. I want to try something new with you guys, which is an actual real life demonstration. So we're going to look at the reflection of flat mirrors. I'm going to open up my camera here, and I set up over here on my desk a piece of paper, as you can see, with a mirror and a laser. And this laser has a button, so I'm going to go ahead and turn it on. All right, so let me make sure my stuff is angled correctly. Check this out. We have our laser coming straight out, for the most part, following along that dashed line into the mirror. Look at what happens to the laser as I start to change. So I'm leaving this guy alone, and I'm changing the angle of my mirror. And notice how that reflected ray kind of goes off in different directions. And they turn it up and down. So what I want to show you is what happens when I take my laser and change that instead. So as you can see, I'm not moving my mirror, but I'm moving my laser. I just angled it a little bit. Make sure it's pointing good, and there you go. So I want you to notice that this angle right here is called the angle of incidence. And this angle right here is the angle of reflection. Now, if you were to have a protractor, you could very, very easily show that those two angles are exactly the same. It doesn't matter how we angle it. So let's say we do it like this, right? Make that angle a little bit bigger. It doesn't matter because this angle, whatever it might be, is going to be exactly the same as this. That, in a nutshell, is the law of reflection. And one more thing that I want to show you is taking a look at the mirror, right? We see how those reflected angles, right? This one's reflected, but we see that there's a mirror image happening over here. And it's literally a line that is traced into the mirror itself, and the same thing happening with that one. So for anything that's reflected in a mirror, if you were to take all of the light rays coming from your light source and trace them all behind the surface of the mirror, you will end up with a very nice representation of the mirror image. And that is pretty much how a mirror works. So let's look at the details of this now. Okay, reflection on flat mirrors. Now, first, I want to draw a line that is normal to the surface of this mirror. So normal is another way of saying perpendicular. So there's my perpendicular line. I'm going to draw an incident light ray and show how it is then reflected, like so. Now, the way that we measure the angle of incidence versus the angle of reflection is, well, let me not say the way that, but rather when you actually go ahead and measure them with a tool, they're always going to be the same value. And that is because the law of reflection states that for any flat mirror or flat mirror-like surface, the angle of incidence, theta I, will always be exactly equal to the angle of reflection, theta R. Okay, the law of reflection. This right here is the big idea of what we're talking about today. Everything that is going to be shown to you is based upon this principle. Let's take a look at how mirror images are formed. Okay, so here I have a flat mirror pointing straight up. and I'm going to place an object in front of it. It could be any object. So for this one, I chose my cat, Jasmine. So Jasmine's sitting here in front of the mirror, right? She's looking into it. And I'm going to pick a random point on Jasmine's head. So let's do it from the tip of her ear. So let's say right here. So we're going to focus on light rays that are going to be emanating from that point on Jasmine's face. So let's look at this one first. That light ray is pointing directly at the mirror, perpendicular to its surface, so it will bounce right back off in the same direction. You guys probably noticed that in the demonstration I just did. I also went and drew some dashed lines that are representative of the rays that are going to form the image. Let's take a look at another one now. Drew another one at some random angle, and it reflected off of the mirror at that same angle, and then I went ahead and traced that line back behind the surface of the mirror too. And let's do one more for good measure. Down there, did the same thing. From the point of Jasmine's ear, drew it to some point on the mirror, reflected it off at the same angle, and then drew a line tracing back into the mirror area of the the image area of the mirror. So if you were to do this for every single point on Jasmine's head and trace it back behind the mirror, you would end up with the image, which looks like this. And that geometry that you see is the reason why their image is then inverted. When you trace all those lines back, they end up giving you a picture that's flipped over, not vertically, but rather horizontally. By the way, this is known as a virtual image. Virtual because it's not really there. We know that Jasmine is sitting there on the left, but that doesn't mean that there's another Jasmine on the right. That's just a reflection, an image that's virtual. It's not really there. Basically, what that means is if we were to put a screen or some sort of thing behind the mirror and place it there, no image will be projected. Later on, we will talk about what kind of mirrors are used to make real images. Think about going to the movies, right? Most movies these days are projected digitally, but back in the early days of film, they would do it with film. So they would shoot light through this tiny little picture that would then blow it up onto a big screen using a series of lenses and mirrors. But we'll talk about that later on in more detail. Okay, let's see another way of how this works. So for this one, I drew a mango, and I picked two random points on the mango, the top and the bottom, and had those 2 points emanate rays that reflected off the surface of the mirror that then bounced towards an area where there's an observer. So like an eye looking at the mirror and its image. So if we were to trace those lines of sight back behind the mirror for all of the points on the mango, you would end up with a horizontally flipped image of that mango. And here's another fact about flat plane mirrors. So let's say that this mango was sitting 3 feet in front of that mirror, right? Due to the geometry of this and the symmetry of this, the image of the mango will appear to be 3 feet behind the mirror. And if that mango was 6 inches tall, that image of the mango would also appear to be 6 inches tall. If your observer was standing in front or right on top of the mango at the same distance, then the image would appear to be twice as far away from the observer. So that's another interesting fact about plane mirrors. Their images are going to be perfectly scaled to the object size, and the distance would be perfectly scaled from the object's distance. So how do you distort image heights and image distances? You have to have a curved mirror. So we'll talk more about that later on. Okay, let's look at a couple of examples of some problems with flat plane mirrors. Let's start with this one. What is the final angle of reflection? So we see we have two mirrors angled 120 degrees apart from each other, right? And we see that the angle of incidence for the initial light ray is 60 degrees. So remember, the main statement that we have to work with here is the law of reflection that says, actually, let me take this off real quick. Remember, super important. The angle of incidence is equal to the angle of reflection. This is the critical piece of information here. Okay, anyway, so we have our incident angle at 60 degrees, our incident ray at 60 degrees. So let's see how that one is going to reflect off of our first mirror. Now you guys can see that I'm angling my ruler here at 30 degrees. That's not a coincidence. So from right there, that looks good. It's gonna bounce off like this. And then hit the mirror again. So let's take this angle off, this ruler off for a second and take a look at this a little bit deeper. Remember, our law of reflection states that the angle of incidence must be equal to the angle of reflection, right? That means that this angle here must be 60 degrees as well. These two need to be equal to each other. And we know that that dashed line is perpendicular to the surface of the mirror. Now, if you remember from geometry, that entire thing, that entire flat surface needs to equal up to 180 degrees. So if that angle of incidence is 60, then that means that this angle down here needs to be 30 to give you the full 90. And then this one has to also be 30. So that all of that adds up to 180, right? 30 plus 60 is 90, plus 60 plus 30 is 180. And because of the law of reflection, we know that the other two angles, the ones below the ray, must be congruent to each other. Finally, let's look at the triangle that was formed inside between the two mirrors and that ray. So we have that angle down there that's 120 degrees and then one that's 30. That gives us an angle, a sum of angles of 150 degrees. So that means that this angle here has to be 30 degrees as well. Because again, all of the internal angles of a triangle must be equal to 180 degrees. All right, let's finish this guy up. Now, at the end, this angle is going to reflect straight up like this. And let's take it one step further. Let's see. Right there. That is going to be our angle that is, our normal line, our perpendicular line. So let's take a look at the geometry happening here. So for this problem, we have some very nice symmetry going on. We see that this is 30 down here, so this must be 60, which means that this needs to be 60. And finally, over here, this needs to be clarity. What is the final angle of reflection? We are looking at this angle right here, the angle of reflection. So in the end, that thing bounces off that second mirror at 60 degrees. But from our point of view, if we're looking at this from the side, it's going to reflect straight up, 90 degrees upward. And there you have it. So for a problem like this one, you have multiple mirrors. You got to use your knowledge of triangles, your knowledge of geometry to solve this type of problem. But as you can see, it's not very hard at all. Okay, let's look at one that's a little bit more tricky. A 5'11" man wants to purchase a full-length mirror. What is the minimum length of mirror that he needs? And I put here on the side so that he can see his entire reflection. And how high above the floor should he hang it? Let's also assume that his eyes are sitting 10 centimeters below the top of his head. Okay, here's how I want to attack this problem. First, the issue that this man is dealing with is that he wants to buy a full-length mirror, right? And he wants to be able to see his full body's reflection in the mirror. But he wants to make it as small as possible. So let's say that the bottom of the mirror is going to reflect right here, and it's going to allow him to see his feet, which is the bottom of his body. And the top of the mirror, right, from right here, is going to allow him to see the reflection from the top of his head, aka the top of his body. Now, we know that the full height of this man is 5 feet 11 inches. So let's use the metric system because that's what we've used all year. 180 centimeters. Okay. Now, from another perspective, from his eyes, which is what he's using to make a measurement, right? From here to here is going to be 170 centimeters because his eyes are 10 centimeters below the top of his head, right? And finally, from here to here, it's going to be 10 centimeters, right? From his eyes to the top of his head. So we're going to use all of those measurements to figure out how big this mirror needs to be and how high above the ground he needs to hang it. And again, to do this, we will use the law of reflection. So the incident light rays coming here from the bottom, that's going to be my theta I, and this is going to be my theta R, and they're going to be equal to each other. That means that that entire height is going to be split right down the middle. We use some triangle geometry here. We would be very easily able to prove that those two angles, right, are congruent to each other, those two triangles, which is going to be a right triangle with that angle theta R, and that side is going to be half of 170, and then for theta I, the side will be half of 170 as well. So we know that part of that mirror is going to be half of 170 centimeters, which is 85 centimeters. So where is that coming from? Again, that's from here to here, and right there to right there. Now let's look at the other piece. The rest of it is going to be from the top of his head to the point where he can see it. However, we have a similar situation going on. This is going to be a little bit difficult for me to draw, but I am going to try regardless. So over here, we have our angle of incidence, and down here, we're going to have our angle of reflection. And the same rationale that we used down on the bottom, we're going to use up here, except instead of 170, now we're going to have 10 centimeters. So half of that is going to give us the side of those two congruent triangles. So we got half of 10 centimeters, which is 5. So the length of the mirror needs to be basically, at the end of the day, half of the man's height, which is going to be 90 centimeters. So here's an interesting result. In general, this is what you got to do. If you want to buy a full-length mirror where you can see your full body and in the reflection, as a rule of thumb, the length needs to be half of your height. So let's say you are 6 feet tall, right? Your mirror needs to be at least 3 feet long. If you are 5 foot, what's half of 6 feet? 5'6", right? Then you would have to have a mirror that is half of that. So let's see, 2.5 feet plus 3 inches, right? Whatever that is, not important. Now let's answer the last part, which is how high above the ground do we need to measure? This part's actually pretty simple because we kind of already did it. Gotta figure out this part, right? Well, we know that from over here, this was 80 centimeters. That means that this guy needs to also be 80 centimeters. And there you go. Sorry, guys, made a mistake. 85 centimeters. And this guy needs to be 85 centimeters. So at minimum, the mirror needs to be 85 centimeters above the floor. So if this guy buys a 90 centimeter high mirror and hangs it up 85 centimeters above the ground, he could stand pretty much anywhere in front of it and be able to see his full body. And we were able to prove that using the law of reflection. So in general, if you wanted to apply this idea to any height, right? Whatever your height is, half of that is going to have to be the length of the mirror. And then you have to have an idea of how far your eyes are from the top of your head. And then half of that is going to be also taken away from the full length of the mirror. And then that's how high you have to hang the mirror. So in this case, our mirror was 90 centimeters. Our height above our eyes, height below the top of our head was 10 centimeters. And half of that was 5 centimeters. So we have to hang the mirror at 90 centimeters minus 5, which is 85. And there are a few other types of problems that we will see. You guys will see it in the homework. I'll probably post that tomorrow. So as always, please don't be shy. Feel free to reach out to me if you have any questions about anything at all. And that is it from me today. Have a great weekend.